Welcome you all to the week 5 lecture of Differential Equation for Engineers. Myself Guru Bachan from Department of Mathematics, IIT Jodhpur. I am working in the broad area of fractal geometry and dynamical systems. In the previous tutorial, we have solved the power series solution around a singular point. So here we will solve that power series around a regular singular point via Frobenius method. So let me write the first question. Solve the following differential equation by Frobenius method. 2x square y double dash minus xy dash plus x minus 5 y equal to 0 in some interval 0 to then r. So we have to solve this given differential equation by this Frobenius method. So let me first recall what is this when this Frobenius method comes into act. So here, if you can observe that from the general differential equation that a naught x y double dash plus a1x y dash plus a2x y equal to 0. So for this kind of equation, we say any point x equal to x naught is a singular point when a naught x is 0 for that x naught. So here, if you will observe, a naught x is 2x square. So clearly put a naught x equal to 0. So this will imply x is nothing but 0. So x equal to 0 is a singular point. So here we came to know that it's a singular point. Now we have to think about whether it is a regular singular point or irregular singular point. So for that, we rewrite our differential equation in the form 1 by 2x y dash plus x minus 5 divided by 2x square y equal to 0. So if you will compare that differential equation from y double dash plus px y dash plus qx y equal to 0, you will get to know that px is minus 1 by 2x and qx is x minus 5 divided by 2x square. So to judge this x equal to 0 is a regular singular point or an irregular singular point, for that we need to check limit x tends to 0 x px and limit x tends to 0 x square qx. These both limits has to be finite for this point to be a regular singular point. So let me check the first one. Limit x tending to 0 x times minus 1 by 2x. So clearly this will give me minus 1 by 2, which is a finite quantity. In the same manner, if we try to calculate this one, x square into x minus 5 divided by 2x square. So it will give us limit x tending to 0 x minus 5 by 2. Clearly this is a polynomial. So polynomial are continuous, so we can directly put the limit. So this will give you minus 5 by 2, which is a finite quantity. So now we came to know that both the quantities are finite. So what we can say? We can say that x equal to 0 is a regular singular point. Okay. Since it's a regular singular point, now we can apply this Frobenius method. So let me recall that Frobenius method is a kind of generalization of this Euler-Cauchy method. In Euler-Cauchy method, we have the differential equation x square y double dash plus xy dash plus y equal to 0. This kind of equation I'm writing in rough language. So its solution will be like this: x to the power c1 x to the power r1 plus c2 x to the power r2. So inspired from this, the Frobenius methods come into act. In this method, what we do, we assume that our power series solution to be like x to the power r into power series to get rid of this regular singular point, or to get the expansion of px on qx. So here, look for yx to be x to the power r summation 0 to infinity cn x to the power n. So we will look for this kind of solution, and then we will put this, we calculate y dash, y double dash, and put into the equation, calculate the values of r by initial equation, and also calculate the, get to know that a recurrence relation between cn, and then we'll try to find this power series solution of this differential equation. So try this one. So let us continue this one. So if you will rewrite this, this is n 0 to infinity cn x to the power n plus r. And here we have given that x is positive, so we are not, no, we are not caring about that x to the power r. Otherwise, we have to take care of mod x. So y dash will be summation n 0 to infinity. We will not change the summation because here is a r involvement involved also in the series. So n plus r cn x to the power n plus r minus 1. Y double dash x will be summation n 0 to infinity n plus r n plus r minus 1 cn x to the power n plus r minus 2. Now we got to know what is yx, what is y dash x, what is y double dash x. Now if we given equation is like 2x square into y double dash x. So that means 2x square y double dash. So what is y double dash here? Y double dash we have calculated like this. So let me write this one. So this is your y double dash x. Next term is in the given differential equation is minus xy dash. So y dash is given here. So this is y1 dash. After this one, we have x minus 5y. So x minus 5y. So this will give summation n 0 to infinity cn x to the power n plus r plus 1. I have opened this, I have multiplied this x, and then I am multiplying with 5. So this will give you summation n 0 to infinity 5 cn x to the power n plus r equal to 0. So first of all, what we have to do, we have to multiply these, and we have to make the powers equal. Here this power is n plus r minus 2. So if you will multiply with this x square, we will get to know that this is nothing but n plus r minus 1 x to the power n plus r. Next, summation n 0 to infinity n plus r, here must be cn x to the power n plus r cn x to the power n plus r. Next is here n plus r plus 1. We want to equalize the power, normalize the power as n plus r. So what we will do, we will substitute n as n minus 1. So after substituting n as n minus 1, we will get here n1 to infinity cn minus 1 x to the power n plus r minus summation n 0 to infinity 5 cn x to the power n plus r. So all the powers of x are same. Now we can find out the recurrence relation and we can discuss the indicial equation. Before that, if you will observe this series starting from n equal to 0, n equal to 0, n equal to 1, n equal to 0. So we have to make them also equal. So for n equal to 0, we do it separate. So it will be 2r into r minus 1. I'm just putting n equal to 0 in this equation. X naught x to the power r minus r c naught x to the power r. Next is here n equal to 1, so we don't need to consider this one. Next is minus 5 c naught x to the power r. So this is your for corresponding term for n equal to 0 from n1 to infinity. This will give you n plus r to n plus 2r minus 2, and here if you minus 1, so this will give you minus 3 minus 5, this times cn minus, or you can say plus cn minus 1, this whole expression x to the power n plus r equal to 0. So you are get to this particular form. Now by putting this x to the power r equal to 0, put coefficient of x to the power r equal to 0. You may also say that we are comparing the powers of x. So you will get 2r minus 2r minus r minus 5 into c naught equal to 0. So from here, you know that this c naught is a non-zero quantity. So c naught is a non-zero quantity because if you will take c naught as some finite quantity, then if you will try to calculate this one, then again the normalized form is same as the previous series. So we will take the assumption from the theory that this c naught to be non-zero without loss of generality. If you will take c naught to be 0, then this series will starting from 1, and here it will be x to the power r plus 1. Again we can take r plus 1 to be r. So therefore, because c naught is non-zero, this will imply 2r square minus 3r minus 5 equal to 0. So this will give you r as, let me just recheck this one, so whether it has been decoded correctly or not. So okay, so from here what you will get, just a second please. So we got this as initial equation. So this is our initial equation. So after this initial equation, we can find out these roots. So what will be these roots? These roots will be 3 plus minus 4 plus sorry, here it will be 9 plus 40 divided by 4. So this will give you 3 plus minus 7 divided by 4. So one of the root will be 7 plus 3, 10, that is 5 by 2, and another one root will be minus 1. Okay, so what we will do, we will assume R1, always R1 to be the greater than R2, just for convention. So R1 is clearly greater than R2, and we will see R1 minus R2 whether it is integer or it is not an integer. So if you will observe here, it will be 5 by 2 plus 1, which will be equal to 7 by 2, which is not an integer. So since it is not an integer, what we can do, we can directly follow up the recurrence relation, and we can put the value of the in the assumed series R as R1 and R as R2, and we can get the solution y1x and y2x. So what is the reoccurrence relation? Reoccurrence relation is here. It is n plus r, 2n plus 2r minus 2 minus 1, that is a minus 3, it will be minus 3, and minus 5 plus cn minus 1. So this is our reoccurrence relation by putting x to the power n plus r coefficient to be 0. So your cn will be, I'm directly writing. So let me first write formally. What was that? Um, so this is your expression for this reoccurrence relation. This is nothing but equal to 0. So from here, but this is valid for n greater than equal to 1. So from here, you can say Cn is nothing but minus Cn minus 1 divided by n plus r, 2n plus 2r minus 3 minus 5. This is your recurrence relation in this particular case. So just let us re-verify it. So here it is n plus r. This is n plus r. If you will take n plus r common, so it will be 2n plus 2r minus 2, and it is minus 1. So 2n plus 2r minus 3. Okay, so it is fine. So next, what we will do, this relation is valid for n greater than equal to 1. So put n equal to 1. What you will get, C1 as minus C0 divided by n equal to 1, and first we are finding out the solution for r1 equal to we have to root 5 by 2 and minus 1. So we have to find out for both. Either what we can do, we can explicitly assume that r1 to be first 5 by 2 and r2 to be minus 1, then we can calculate it, or otherwise we can calculate for general r, then we have to solve it. So I am doing for first of all 5 by 2. So r1 equal to 5 by 2, what it will give? So it, and n equal to 1, we are saying that, so it will give you 1 plus 5 by 2. So this will be 2 plus 5 minus 3 minus 5. So this will give you minus C naught divided by 7 by 2 into, this is 5 plus 2, 7 minus 3, 4. That is nothing but 14 minus 5. So this will be minus C naught divided by 9. So we got C1 in terms of C naught. Now put n equal to 2. So for n equal to 2, we will get C2 as minus C1 divided by 2 plus 5 by 2 into 4 plus 5 minus 3 minus 5. So this will give you minus C1. So 9 by 2 into 9 by 2 into this is 5 plus 4, 9 minus 3 is 6. So this will give you 27 minus 5, that is minus C1 divided by some 22. And since C1 is nothing but C0 divided by 9, so it will becomes positive. So it will give you this much. Now you calculate C0, C0, C0 and C1, C2. You have calculated. In the similar fashion, you can calculate C3 and C4. So I'm explicitly writing y1x to be x to the power r1, that is 5 by 2, and series was starting from C0 plus C1x. What is C1x? Minus C0 by 9x plus C0 divided by 198 x square minus and dot dot dot. Since this sign was positive, other sign will be, so this sign was negative, then other sign will be positive, then again it is coming out to be, it will come out to be negative. So for convention, what we can do, we can assume it to be 1. So x to the power of 5 by 2, since it's arbitrary constant, 1 minus x by 9 plus x square by 198 minus and so on. So what is your y1x if I would write without arbitrary constant? So this is this much, 1 minus x by 9, x square 198, and this is the your y1x. We have not completed yet because we have to calculate the same thing with respect to the R2. What is your R2 here? R2 is minus 1. Here R2 is minus 1. So we have to use this recurrence relation for R2. So let us calculate for R2 also. This is the recurrence relation for R2. What we will do, we will put n equal to 1, and what happened? C1 will be minus C0, and since R2 is minus 1, so it will be minus 1, 1 minus 1, 1 minus 1 into another one will be 2 minus 2 minus 3 minus 5. This will give you minus C0. This quantity will be 0 and less will be minus 5. So this will be C0 by 5. Now put n equal to 2. This will give you C2 as minus C1 divided by. So 2 minus 1 into 4 minus 2 minus 3 minus 5. This will give you minus C1. So this will give you 1, and this is 3 minus 2 5, and 5 minus 4 is minus 1. So this will give you minus 6. So this will be your 6. So in the same way you can calculate C3, C4. So y2x will be x to the power minus 1, that is R2, C0 minus C1 is C0 by 5. So it will be plus C0 by 5x plus, since it is C1 by 6, and what is C1? C0 by 5. So it will be C0 by 30. So it will be C0 by 30 x square and so on. So again, if you will write by assuming that C0 to be 1, so your power series is 1 plus x by 5, x square by 30, and so on. And your general solution will be yx is equal to some d1 times y1x plus d2 times y2x. So if you will write it explicitly, d1 times, what was your first solution? It was x to the power 5 by 2, 1 minus x by 9, x squared by 198, x by 9 plus x square by 198 and so on, plus d2 x to the power minus 1, 1 plus x by 5 plus x squared by 30. This is your final y2. This is your final y2, general solution. Yx is the general solution of the given differential equation. So this is our given, it is our general solution for the given differential equation. In the next question, we do such a similar approach for this differential equation. So for use Frobenius method to solve the differential equation 2x square y double dash plus xy dash plus x square minus 3y equal to 0 in some interval 0 to r. So again, for this question, if you will observe that x equal to 0 is a regular singular point, so I'm not calculating here, I will write directly. So here x equal to 0 is a regular singular point. So if it is a regular singular point, so by Frobenius method, look for solution yx equal to summation n0 to infinity cn x to the power n, and here x to the power r will be outside. So with assumption c naught should be non-zero. So y dash x will be x to the n 0 to infinity, so cn n plus r x to the power n plus r minus 1, and y double dash x will be summation n0 to infinity n plus r n plus r minus 1 cn n plus r minus 2. And if you will put these values into the given differential equation, you will get summation n 0 to infinity 2 times of n plus r n plus r minus 1 cn x to the power n plus r. Since x square was there, so it will become n plus r, plus summation n 0 to infinity n plus r cn x to the power n plus r. Next is summation n 0 to infinity cn x to the power n plus r plus 2 minus summation n 0 to infinity 3 times of cn x to the power n plus r equal to, this is your final after putting this value. Now we will, our target is to make all the powers of x same. So we will substitute here n minus 2 in place of n, and you will get summation n0 to infinity. If you will combine these first two terms, so what you will get 2 times, or you can say n plus r. So this is 2n plus 2r minus 2 plus 1. So this will be 2n plus 2r minus 1 cn minus 3. So let me write cn outside. So cn x to the power n plus r, and other series will be summation n 2 to infinity So since I'm putting n as n minus 2, so the series will start from n equal to 2. So this is your final series. So since it's starting from n equal to 2 and it's starting from n equal to 0, so we take out from these terms for n equal to 0 and n equal to 1. So it will happen like r 2r minus 1 minus 3. This times c naught x to the power r plus for c1 you will get 1 plus r into 2 plus r minus 1 minus 3. This much times c1 x to the power r plus 1, and the rest part will be in this n equal to 2 to infinity n plus r 2n plus 2r minus 1 minus 3. This much times of cn min plus cn minus 2 x to the power n plus r equal to 0. So from here, if you will put x to the power coefficient of x to the power r equal to 0, you will get the initial equation in the form 2r square minus r minus 3 equal to 0. This will be your initial equation. So how you are getting it? Coefficient of x to the power r equal to 0. So this will give you r equal to 1 plus minus 1, say it will be plus 4 2s are 8 3s are 24 divided by 4. So this will give you 1 plus minus 5 divided by 4. So this will give you 1 plus, if it will be plus, so 6 by 4, that is 3 by 2, and if it 1 minus, so it will minus 4, that is minus 1. So again we will assume r1 to be 3 by 2, it should be greater than r2, and r2 to be minus 1, and r1 minus r2 will be nothing but 3 by 2 plus 1 will give you 5 by 2. Clearly this is not an integer, so we can follow up in the similar manner like the above case. So we will take the help of recurrence relation that is given in this equation. So this recurrence relation will give us recurrence relation. I'm writing in the short form. So this is will be Cn equal to Cn minus 2 divided by n plus r 2n plus 2r minus 1 minus 3, and this relation will be valid n greater than equal to 2. And moreover, we may see like this also. This is n plus r minus 1, so we may write it as 2 times of n plus r whole square and minus times 2 times of n plus r, and this will be n plus r. So for simplification we may write like this also. So I am writing this form also, that Cn can be also written as Cn minus 2 divided by 2 times of n plus r square minus n plus r minus 3. So it was like that only. Yes. So this relation is valid from n greater than equal to 2. And there is one more term involving that first term, that is this one. So what it will imply, anyway this is a constant, and this is then it will imply C1 to be 0. So 1 plus r. So here coefficient of x to the power r plus 1 equal to 0. So this will give you 1 plus r, 2 plus r minus 1. Here I am putting n equal to 2, so it will be 2r. So 2 plus 2r minus 1, c1 minus 3, c1 minus 3, c1 equal to 0. So this will imply c1 to be 0. Okay. Now use the recurrence relation. Put n equal to 2. What you will get? C2 as minus C naught divided by and we are finding the solution for r equal to we have 2 roots 3 by 2 and minus 1. We are finding for 3 by 2. So for r equal to 3 by 2, what you will get? You will get 2 plus 3 by 2 whole square minus 2 plus 3 by 2 minus 3. So let me write it as I have solved it. So I'm right since I've calculated, so I'm writing it directly. So this will give us, so this is nothing but 7 by 2, that is 49 by 4 into 2, that is 49 by 2. So this will give you minus C naught divided by 18. Now put n equal to 3. So n equal to 3 give you C3 equal to minus C1 times divided by that relation. So this is 2, 3 plus 3 by 2 whole square minus 3 plus 3 by 2 minus 3. So since C1 is 0, so this will be going to be 0. Next, C4 will be minus C2 divided by 2, 4 plus 3 by 2 whole square minus 4 plus 3 by 2 minus 3. So this will give you minus C2 by 52. And since C2 is C naught by 18, so this will be C naught by 18 into 52, which is 936. Okay. In the similar fashion, if you calculate C6, you will get minus C naught divided by 95472. Now you got to know about your y1x, that is with respect to r1 equal to 3 by 2. So x to the power 3 by 2. I am already missing c. I am taking c naught to be 1. If c naught to be 1, so first will be 1 c naught plus c1x, and c1x is 0, and c2x is c naught by 18, that is x by 18, x square by 18, since it's a value of c2. So plus next one is C naught by 936, that is x to the power 4 by 936 minus x to the power 6 by 95472 plus dot dot. Okay, this is your first series solution, and for the second one we will take for r equal to minus 1. So for r equal to minus 1, if you will put in this relation and you will put the values of n, then you will get your C2, C4 in the following form. C2 will be C naught divided by 2 times of n equal to 2 we are putting. So 2 minus 1 whole square minus, and this will be 2 minus 1 minus 3. So this will give you C naught divided by, I think this was the relation, 2n plus r square. So we are putting n equal to 2 and r is nothing but minus 1. So yeah, r is nothing but minus 1. So 2 minus 1 whole square minus 2 minus 1. So this will give you 2. This was with negative sign, and minus 1 minus 3, which will be C naught by 2. Similarly, C4, C3 is some multiple of C1, so it will be with negative sign. With negative sign, this will be 2 times of 3 minus 1 whole square, 3 minus 1 minus 3. So this is ultimately will be 0, since C1 is 0. Now C4 is minus C2. divide by 2 times of 4 minus 1 whole square minus 4 minus 1 minus 3. This will give you minus C2 divided by 3, 9 to the 18 minus 3 minus 3. So this will be minus C2 divided by 12. So since C2 is C naught by 2, so this will be minus C naught by 24. Okay. In the similar way, if you will calculate C6, you will get C naught by 1008. So if you will write y to x, this will give you x to the power r, that is x to the power minus 1, and I am taking C naught to be 1. So your solution will be 1 minus, or it is plus x square by 2 with negative sign, x to the power 4 by 24 plus x to the power 6 by 1008 with negative sign, so and so. So your general solution will be yx will be d1 times of your first solution, and your first solution is x to the power 3 by 2, x to the power 3 by 2, 1 minus x square by 18 plus x to the power 4 by 936 minus x to the power 6 by 95472 and so on, plus d2 x minus 1, 1 plus x square by 2 minus x to the power 4 by 24 plus x to the power 6 by 1008. So this will be your general solution of the given differential equation. So till now we have only seen the case when your R1 minus R2 is nothing but its difference is not an integer. Now the natural question arises, there might be some cases for which this R1 and R2, R1 minus R2 can be 0 or can be an integer form. So what we will do in that case? So for that we'll do some illustration on behalf of that also. For that, let me write your third question. Question number 3. Use Frobenius method use Frobenius method to solve the differential equation. And let me write the question. Let me write the differential equation. So differential equation is the second piece. So here is the differential equation that contains. So this is the particular case of integer. So for that, x y double dash plus y dash minus xy equal to 0, and here x is greater than 0. So for this case we have to find we have to apply the Frobenius method. So how we can apply, let us see that. So it is clear that x equal to 0 is a regular singular point. Okay, so if it is a regular singular point and you will put the values of this y dash, so you will look for yx to be summation n0 to infinity x to the power r Cn x to the power n plus. So this we will calculate now y dash, y double dash, and you will put into the given differential equation. Then try to find out the value of r with the help of initial equation, then recurrence relation. Use the recurrence relation to find the solution. So try this one, then we will discuss. So what will be its first derivative? So its first derivative is summation n 0 to infinity Cn n plus r x to the power n plus r minus 1. While the second derivative will be n plus r. Okay. Now we'll put these values in the given differential equation. You will get to n plus r n plus r minus 1 Cn plus n plus r Cn x to the power n plus r minus 1. And the last one will be summation n 0 to infinity Cn x to the power n plus r plus 1 equal to 0. So Here the power is n plus r minus 1 and n plus r plus 1. So we need to first make these powers same. So what we can do, we write it as n 0 to infinity n plus r into n plus r. We can also made it n plus r. So if you will want to make it n plus r, what we put n as n plus 1. So this series will be starting from n minus 1. So since if this series will start from n minus 1, so we may avoid that step also, and we will directly conclude that this is n plus r and n plus r minus 1, and this is adding, so you will get n plus r whole square Cn x to the power n plus r minus 1, and try to make it as n plus r minus 1. So we will put n as n minus 2. So the series will start n2 to infinity Cn x to the power n plus r, and it will be, since we are putting n as n minus 2, Cn minus 2 equal to 0. So from here, this has series starting from n equal to 0, and this series from starting from n equal to 2, we will get we will put n equal to 0. So first n equal to 0 give you r square c naught x to the power r minus 1 plus, next add n equal to 1, r plus 1 square c1 x to the power r. We're putting n equal to 1. So x to the power r minus, in fact plus. So 2 to infinity. Now you may combine n plus r whole square cn minus cn minus 2. This series x plus n r minus 1 equal to 0. Now the first term will give you in the cell equation, that is r square equal to 0. That means r equal to 0, 0. That is roots are repeating. So what we will do, we will first find out the solution with respect to r1 equal to 0. Then I will let you know how to find out the other solution, other linearly independent solution. So the next term will give you r plus 1 whole square c1 equal to 0. Clearly this is a non-zero quantity. So what this will imply? This will imply c1 to be 0. Now the third term will give you the recurrence relation. So recurrence relation will be cn equal to cn minus 2 divided by n plus r whole square. So if you will think it as n plus r whole square, so what will your, this is n greater than equal to 2. So n equal to 2 give you c2 divided by c naught r plus 2 whole square. I'm writing in terms of r directly. So this will give you c2. So since we get c2, so c3 c1 divided by r plus 3 whole square. Since c1 is 0, then this will be 0. Next is n equal to 4, and c4 will be c2 divided by r plus 4 whole square, and c2 is c naught divided by r plus 2 whole square. So this will be whole square, and again n equal to 5, c5 will be some c3 divided by r plus 5 whole square. This will be 0 since c3 is 0. Now you get to know that how the series is moving. So you may write for general r. I'm writing this one y1 x for general r. So this will be x to the power r. I'm taking c naught as 1, and your c2 will be 1 plus x square divided by r plus 2 whole square plus x to the power 4 r plus 2 whole square r plus 4 whole square, and so on. Okay. This is your first solution if you will put an r equal to 0. So first solution will be y1x when you put r equal to 0. So this will be x to the power 0, 1 plus x square divided by 2 square, x to the power 4 divided by 2 square into 4 square, and this will continue. How to find out this for the other Li solution? So one approach has been told you in the lecture is that consider y2x to be pi1x ln x plus x to the power r2. Here r2 is nothing but 0. So summation n1 to infinity dn x to the power n. So you need to find out here, let me just confirm it. Yes, it is correct. So we need to find out here this unknown constant dn. One approach is this that involves a little hard more calculation. So another one is you have find out this y1 in terms of r or x. So what you will do, you will partially differentiate with respect to r, and you will put r to be 0. Sorry, so you will put r to be 0. So if you will differentiate partially with respect to r, so what you will get partially, first of all, let us differentiate partially with respect to r. First term is x to the power r ln x by product rule, and the series will remain same, 1 plus x square r plus 2 whole square plus x to the power 4 r plus 2 whole square r plus 4 whole square, and so on. And the other one will be x to the power will be as it is, and you have to differentiate with respect to r the other term, 1 plus, or you can say 1 minus x square r plus 2 whole cube x to the power 4 divided by, you will get two terms here. So this will be minus 2 r plus, and here is r plus 2 whole square and r plus 4 whole square. You have to differentiate two times and then you have to put r square. So let me write it. So this will correspond to plus minus 2 by r plus 2 cube minus 2 by r plus 4 cube, and this expression will go on. To find out y2x, this will be del y1 x and r. You will put x and r as 0. If you will put r as 0, it is your solution ln x 1 plus x square by 2 square x to the power 4 2 square 4 square, and so on, plus x to the power 0 1 minus 2x square divided by 2 cube. So if you will write it as, it will be 2 square. So and here plus x to the power 4, this will be 1 by 2 cube, so minus 1 by 4, or you can say 1 by 2 square minus, and the other factor will be 1 by 2 into 2 cube. So if you will solve this one, what you will get, ln x 1 plus x square by 2 square x to the power 4 by 2 square into 4 square, and this series will be 1 plus x square by 2 square. So if you will not solve this one. So what you will get 2 cube and 4 cube. So you have to solve this one anyway. So 1 by 4 plus 1 by 16. So this will be 5 by 16. So 5 by 16, or you can say 2 to the power 4 with negative sign, x to the power 4, and this expression will solve. So you will get this series, and what is your combined general solution? Yx to b some d1, and this first one solution. If you observe that this first ln x multiplication term is also y1x, so you can write d1 plus d2 ln x, and this series, and d2 times of the other series. So this will be your general solution of the given differential equation. So let me just verify this answer, so whether it is written correctly or not. So this is 1 minus x squared by 2. So we need to differentiate with respect to r. So there is just a small error. So this constant term will go. So this will be, yeah. So this series will be starting from this. So this will be, and obviously minus sign will be there. Minus sign will not go. So minus x squared by 2 square minus 5x by the power 4. Okay. So this was your solution for this given differential equation. Now let us consider the task where the difference of these roots of the initial equation is integer. So solve x into 1 plus x 3x y dash plus y equal to 0 around x equal to 0. So try this one. So again, x equal to 0, regular singular point. So we will look for yx to be where c naught to be non-zero. Okay. So y dash x will come out to be n plus r cn x to the power n plus r minus 1. Y double dash x will be n plus r n plus r minus 1 cn. So if you will put these values in the given differential equation, you will get, I'm solving a letter in the indirectly manner. So this will be n plus r minus 1 cn x to the power n plus r minus 1 plus summation n0 to infinity n plus r n plus r minus 1 cn n plus r plus summation n0 to infinity 3 times of n plus r cn x to the power n plus r plus y summation n0 to infinity cn x to the power n equal to 0. Clearly, all the powers of x are not equal, so we have to make here put n as n plus 1. So this series will start from n equal to 1. So n 1 to infinity n plus r plus 1 n plus r cn plus 1 x to the power n plus r plus summation n0 to infinity. If you will combine these terms, so this is n plus r, this is n plus r minus 1. So this will give you n plus r whole square minus n plus r, and this is 2n plus r plus 1 c n x to the power n equal to 0. So if you will put n equal to 0 in this equation, you will get r square plus 2r plus 1. Let me check whether we have written correctly or not. So this first term is plus 3 minus lambda. Yes, till now it is correct. And plus lambda whole square minus n minus lambda plus 3 times of this. So this will give you plus 2 times of n plus r. Next term is, so I think this is correct. So from here, n equal to 0. So we have put in this term. If you will explicitly write also, from the above expression, r into r minus 1 c naught, from the lower part, r 3r c naught plus c naught. So this will give you r square minus r plus 3r plus 1, that is r square plus 2r plus 1 equal to 0. Again, we are coming to that step. So I think the calculation is correct. Here, the next one will be n1 to infinity n plus r whole square. If you will observe here, this is nothing but n plus r whole square, and this is n plus r, 2 times of n plus r, so n plus r plus 1 whole square, Cn plus n plus r plus 1 into n plus r, Cn plus 1 x to the power n plus r equal to 0. Okay, so the first term will be giving you 2r plus 1 equal to 0. So this will be r is minus 1 and minus 1. So both the roots are same. So and your recurrence relation will be Cn plus 1 equal to minus n plus r plus 1 divided by n plus r into Cn for n greater than equal to 1. So this is our recurrence relation. So n equal to 1, we will get C2 as minus r plus 2 divided by r plus 1 C1. So sorry, this relation will be going to start from, this should be start from n equal to 0. So let me just recheck it. So this is n plus, we are putting n as n plus 1. So this must be starting from n minus 1, since we are putting n as n plus 1. So since it is starting from n minus 1, so our we have made a little mistake. So our first, there is one more term, and this series will start from n equal to 0. So there is one more term that is for n equal to minus 1. So n equal to minus 1, you will get r into r minus 1 c naught, and since it is starting from 1, so it will be c1 plus x to the power r. So this will be c naught r into r minus 1 c naught plus x to the power r minus 1. So this is your lowest degree term. So this lowest degree term imply the case that you have two different roots, but their difference is an integer. So r must be 0 and 1. So initial equation will be come out to be r is 0 and 1. So from here you will take r1 as 1, r2 as 0. So this will imply r2 minus, sorry, r1 minus r2 is 1, which is an integer. So what you will do, you will first find the solution with respect to r1 equal to 1. Then we will think about what to do, how to get the other solution with respect to r2 equal to 0. So from here, so do we need to write this expression explicitly? So no, we can directly move this to this. So we don't need to write this one. We can directly now say this is from n greater than equal to 0, or if you will write a little more precise way, 0, 1, 2, and so on. So this will give you, first is C1 C0. Okay, the second is r plus 2 divided by r plus 1. Since we are putting n equal to 0, so n equal to 0, it will give r plus 1 divided by r. So this will be r plus 2 divided by r plus 1 C1, which is minus r plus 2 divided by r C0. Next is C3, r plus 3 divided by r plus 2 C2. So this was minus, so this will become positive. So next expression will be r plus 3 divided by r into C naught. R plus 2, R plus 2 will cancel out, divided by R. So your y1x in terms of R, this will come out to be x to the power R C naught, that is we are taking C naught to be 1 plus C1 R plus 1 divided by R x to the power 1 plus R plus 2 divided by R x 2 and so on. Now again we will find out one solution is put by putting R1 as directly 1, and another solution is by differentiating this with respect to R. This means xr, and put R2 equal to 0. You will get the other solution. So first of all, let me partially differentiate with respect to R. One is x to the power R ln x, and this expression will be remain same, and another one is to differentiate the other part. So this will 1 is 0, so this will give you 1 by r square, 1 plus 1 by r, so minus 1 by r square. So this will give you x by r square. Another term will give you minus uh, 2 by r square x square, plus it will be 3 by some r cube. It will be minus sign, so r cube not r square x cube and so on. So like this you will get the another solution for r equal to 0. Okay, del y1 del r x r equal to 0. So this will be x 0 ln x, and your this series, that is 1 minus r plus 1 by r x r plus 2 divided by r x square minus and so on. So since we are putting r as 0 here, so what you will get, let us just rewrite it here. This is all r, so but we can possible here, since we want to put r equal to 0, so r equal to 0 make it is undeterminate form. So what we can do, we can take a naught to be lambda times a naught, so that this r will be manageable, or otherwise you may find out the simply do the calculation. There is one more approach I forgot to mention here. Another one is to find out y2x as some a, that is told in the class, some a y1x ln x plus summation x to the power r2 summation n 0 to infinity dn x to the power n. So this is the another way to find out solution, and a will you have to find out an and dn here are unknown constant from this equation. So in this manner you can do this one also. So here what I can do smartly, I can take that c naught to be some r times c naught. So this will give you some kind of this can save you, since it is coming out to be indeterminate form. So we have to follow up this approach, and we have to find out the unknown coefficient a and dn. This is the broader approach I am telling you. So you may do this one by yourself. So from here we cannot follow up because undeterminate form. So you have to follow this one. So let me write the next question. This was, I think, question number 4. Question number 5 is find the Frobenius solution of the for x greater than 0. So for this question, you have to find out its Frobenius solution. Try this one, then we will discuss it. So let us start. So again, x equal to 0 is a regular singular point, and yx is you have to see yx as and y dash x will be en. So if you will multiply x square with y double dash x and 6x with y dash x, you will get n star plus. If you will multiply this x square, you will get n plus r plus 2 equal to 0. So to get to n plus r, what you will do, you will substitute n minus 2, and you will get here the series will start from n to infinity x to the power n plus r. So from this, all the powers has become the same, but the series is starting from n to infinity. So you have to combine these terms, and you have to explicit for that write n equal to 0 and n equal to 1. So for n equal to 0, you will get r into r minus 1 plus 6 times of r plus 6 c naught x to the power r. Next is r plus 1 into r plus 6 times of r plus 1 plus 6 c1 x to the power r plus 1. Now for n to infinity, you will get n plus r whole square minus, in fact, plus 5n plus r plus 6, this times cn plus cn minus 2 x to the power n plus r equal to 0. So this will give you the initial equation r square plus 5r plus 6 equal to 0, and r will be minus 2 and minus 3, and you will assume r1 to be minus 2, r2 to be minus 3. Now r1 minus r2 will be 1, which belongs to an integer. So for in this scenario, what you will do, you will now follow up this second term. From the second term, you will get c1 to be directly 0, because this quantity is nothing but a non-zero quantity. So cn is with negative sign cn minus 2 divided by n plus r whole square 5 times n plus r plus 6, and this will be 2, 3, and so on. So from here, when you will put n equal to 1, I mean 2, c2 will be c naught divided by r plus 2 whole square 5 times of r plus 2 plus 6. Or you may write some explicit form, since it will be a minus c naught. You may also write that this is r plus 2. If you will factorize it, you will get r plus 2 plus 3 and r plus 2 plus 2. So r plus 5 into r plus 2 plus 3 r plus 4. This kind of thing. Okay. So I think it is correct. I think yes. So, okay. So your first term will be r plus 5r plus 4 for n equal to 3. This will be C3 divided by C1 into r plus 3 whole square plus 5 times of r plus 3 um, plus 6. Since C1 is 0, then it will be 0, and n equal to 4 will be C4 minus C2 divided by, again, so if you will write it here, this will be nothing but n plus r plus 3, n plus r plus 2. So this will give you, for n equal to 4, r plus 7, r plus 6. And if you'll combine with this value of C naught, so this will be from 7, r plus 6, r plus 5, r plus 4 till there. So if you will write r plus 4 plus I, where this multiplication starts from 0 to up to which thing? 4, 5, 6, 7. That means last one will be 3. So this series will go on. C5 is again 0. Then you have to calculate C6. So your one solution will come out to be yx to be x to the power minus 2. C naught we are taking 1. So it will be 1 minus 1 minus, and this is C value of C2, x square r plus 5 r plus 4. Next solution will be x to the power 4, and this multiplication from 0 to 3 r plus 4 plus I, and this is so on. So you got one solution from here. Now what you will do, you will partially differentiate this with respect to this r, and you will put r equal to minus 3. So if you will partially differentiate with respect to r, so this is x to the power minus r, so x to the power r ln x. So one solution, this is as it is, and another solution is x to the power r. You will differentiate this minus, so this will give you r plus 5 whole square, r plus 4 whole square into the differentiation of this r plus 5 and r plus 4, which will give you uh, r plus 4 plus r plus 5, that is 2r plus 9 x square plus. In the similar way, if you will do the other differentiation, you will get some quantity, and which is like that I 0 to 3 r plus 4 plus I, this whole square, and this will be negative sign, so this will be positive sign, so negative sign, so you will get r plus 4 plus I, r plus 4 plus 0, r plus 4 plus 1. So like that you will get the quantities of the multiple. If you will explicitly write it, you will you will get, for example, first term will be r plus 4, r plus 3, um, or if you will differentiate first term, r plus 7 plus the addition of r plus 4, r plus 6, r plus 7, and the other term will be r plus 4, r plus 5, r plus 6, and the last term will be, I think all of them done. There are 4 times, so it will be 3 times of differentiation, 5, 6, 7. We have differentiated all the terms. So this kind of relation you will get, and you have to solve this one and put r equal to 2. So at the end, you will get some solution, yx equal to c1 plus d1 plus some d2 ln x into the first series that you got, x to the power minus 2, 1 minus x square plus you have to put n equal to minus 2, r equal to minus 2 here. So 6 I'm just writing answer. You may verify it. 3 by 10 dot 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 plus d2 x to the power minus 2 5 by 5x squared by 6. I'm writing only this term where d1 and d2 are arbitrary constant. So this is your case of integer when you have the difference integral equation difference roots difference is integer. So next question is solve the differential equation x square y double dash plus xy dash 4x square minus some new square y equal to 0. Clearly, this is a kind of you can say this is a type of Bessel's equation. So you need to solve this by some transformation of x. Try this one. So let us do the substitution, or you can say the transformation, to convert this into the Bessel differential equation form. So what we will do, we will try to put z equal to some 2x. If z equal to this some 2x, what you will get? You will get dy by dx to be dy by dz, dz by dx. So it will be 2 times of dy by dz. In the similar way, d2 square by dx square you will get as 4 times, if you will differentiate d by dx of 2 times of dy by dz. So 1 you will get 2 times of d2y by dz square and dz by dx. So this will give you 4 times of d2y by dz square, and minus, um, that's all you will get. Uh, you will put these values into the given differential equation and you will come up to 4 times of x square d2y by dz square. Since we are putting x as z by 2, so this will be z by 2 whole square into 2. So plus 2 times of z by 2 dy by dz plus z square minus mu square to z equal to 0. So here we are just changed the independent variable x by z. So you will come up to z square d2y by dz square plus z dy by dz plus z square minus mu square y equal to 0. So this is your Bessel equation in the form of z, where this n is replaced by nu. So if you will compare it with the Bessel differential equation told you in the class, then you will get that in that differential equation is like this: x square minus alpha square is equal to 0, whose solution is yx is equal to c1 j alpha x plus c2 j minus alpha x. So where j alpha x is, let me write it explicitly, x to the power alpha 1 plus summation m1 to infinity minus 1 to the power m x to the power 2m divided by 2 to the power 2m into m factorial alpha plus 1 to alpha plus m. So this is your j alpha x. And if you want to calculate, if you want to find out with j minus alpha, so you just need to put minus alpha in this j alpha x. So here your y z will be, since we have transformed the independent variable, y z will be c1 j nu z plus c2 j nu minus mu z, and your yx will come out to be c1 j nu 2x plus c2 j minus mu 2x. So if you will, I will write explicitly what is j nu 2x. It will be 2x to the power alpha 1 plus summation m1 to infinity minus 1 to the power m. Since it is 2x to the power 2m and divide by 2 to the power 2m, so 2m will be 2 to the power 2m will be cancel out. So the left part will be alpha plus 1 to alpha plus m. Similarly, if you want to write a g minus mu, you just need to replace here. It should not be alpha since we are talking about mu. So similarly here also, so this series will be nu plus 1 to nu plus m. So this will be your solution to this given differential equation. In the similar fashion, let me give you one more question. Solve the differential equation x square y double dash minus 3x y dash 4 x to the power 4 minus 3 y equal to 0. This is also a similar kind of equation. Try this one, how you can convert, how you get to the step of Bessel equation, Bessel differential equation. So let us start to get to the general classical Bessel differential equation. So for this, what we will do, we will first put the independent variable as z as, put z as x square. So your dy by dx will be dy by dz, dz by dx. So what will be your dz by dx? This will be 2x, or you can say the value of x will be under root z, to 2 under root z dy by dz. Next is d2y by dx square. So this will be d by dz of this quantity, that is 2 under root z dy by dz into dz by dx. So dz by dx is, so this will give you 1 by under root z dy by dz plus, and this will give you 2 under root z d2y by dz square, and dz by dx is nothing but 2 under root z. So this will be 2 times of dy by dz plus 4 times of z d2y by dz square. So if you put these values in the given differential equation, you will get, so it was x square. So x square is nothing but z into 4z d2y by dz square plus 2 times of dy by dz minus 3 times of under root z and 2 times of under root z. So it is 3. Okay. So dy by dz plus 4 times of, we are doing this because here it is x to the power 4, so we want here z square type of term. So this will be z square minus 3y equal to 0. So from here you will get 4 times of z square d2y by dz square. Here it will be 2z, it will be 6z. So the left part is 4z dy by dz plus 4 times of z square minus 3y equal to 0. Now if you will observe that still you didn't come up to the classical differential Blaisdell differential equation. The reason is here it is minus sign. This sign should be positive. So what you will do, you will substitute, you will set y as some z times of u. Then y dash meaning dy by dz. So dy by dz will give you u plus u is a function of z. It's obvious. So this will give you u du by dz, and the second differentiation will be du by dz. So 2 times of du by dz z dtu by dz square. So you will put these values into the given differential equation to reach the classical Bessel differential equation. So this will give you uh, z square into z u double dash plus 2 u dash. So minus z of u plus z u dash plus z square minus 3 z into u equal to 0. So if you will solve it, you will get z square u double dash plus 2 times of z square u dash, and from here 2 times of let me write it, then only it is easy to see, 2z u dash minus zu minus z square z square u dash plus z cube minus 3z u equal to 0. Now from this there is one more term 3zu, so it will become 4. So if you will solve it, you will get z square u double dash but plus z square like z u dash. I am taking z to be common, and this will give you plus z square minus 4 u equal to 0. So this is your classical differential equation now. And what is its solution? As I told you earlier, u of z will be nothing but some c1 j 2 z plus some c2 j minus 2 z, and your y of z will be z times u, that is c1 j2 of z plus c2 j minus 2 of z. and yx will be, since we have taken z as x square c1 j2 of x square plus c2 of j minus 2 x square. So this will be your final solution of this given differential equation. And this j2 x square from the above expression you can explicitly write as x to the power alpha, that is x to the power 2, 1 plus series from m0 to infinity minus 1 to the power m. It is x to the power 2m. So here x square, so x to the power 4m divided by 2 to the power 2m, and the other expression is m factorial. So the expression is alpha plus 1 to alpha plus m. So alpha is here 2. So it will be starting from 3, 4 up to alpha plus m. That means m plus 2. So this expression will go like this. Okay. So I'm giving one last question related to this Bessel form. So find the general solution of the differential equation x square y double dash plus xy dash plus x square minus 1 by 16 y. So obviously it's directly classical Bessel differential equation. So try this one. So since it is a classical Bessel differential equation with alpha equal to 1 by 4, so here from the classical differential equation alpha is nothing but 1 by 4. Your solution of this is nothing but c1 j 1 by 4x plus c2 j minus 1 by 4 of x, where this j1 by 4 of x is your solution, which is like this: x to the power 1 by 4, 1 plus m 0 to infinity minus 1 to the power m, x to the power m by 2, 2 to the power 2m, m factorial. Since it is alpha plus 1 to alpha plus m, so it will be 5 by 4 into 1 by 4 plus 2, that is 9 by 4, and so on up to m plus 1 by 4, alpha plus m. So this is your final general solution of this given differential equation. So that's all for today's lecture tutorial. So if you have any doubt, you may ask. So since it is not, thank you for joining. We'll meet in the next tutorial on next Tuesday. Thank you.